they say these functions have uniform weight k. So weight is the number of iterations in these integrals. And well, iterations or what? The integration kernels which we can have follow from what's written on the right hand side of the differential equations. So there are those integration kernels here. Which specific ones depends on the singularities of our functions. And also to repeat some terminology, this is usually called the alphabet of those polylogarithms. Good. That's the summary from last time. Now, also, we had in the discussion of the singularities, I gave this example. I went through it to check. It almost worked, but now here's a version which actually does work. So I modified slightly the original matrix in this example. So you see here we have one term which has the right singularity structure, but there's one which has a spurious singularity at 0. The singularity is too high. And one can define this gauge transformation matrix to remove it. And then you can check if you put it in, you get the canonical form of A prime. So that's just to correct that. And okay, so now what's the plan for the last lecture? First I'd like to tell you about the extension to multiple variables. Actually, after we've done this work of getting so far, this is now one of the strong points of the method. This will be very natural and very simple. So I'll do that. And then another important point, I'll tell you about how to find this uniform weight basis in practice. It's actually very simple, and as I said already, it's kind of the approach that I use most is actually orthogonal to the one that we had before. So the previous lecture was more to motivate from the point of view of the singularities what happens, and now we're going to take a somewhat different approach based on which is more graph-based. And then there are two other topics which, depending on time, well, I definitely want to mention them, but how much details I can give will depend on the time. This first one is especially relevant for n equals 4, so there's other let's say special cases where one is actually interested in certain finite quantities at the end of the day. Say you want to compute correlation functions in a finite conformal field theory, then you don't really care about all this epsilon dependence. So you want to compute something which is manifestly finite in 4 dimensions. So then of course you can use this approach as exactly as we discussed it, but you're actually computing way too much because you compute this whole infinite epsilon expansion. So you might guess that there are simplifications if you can restrict yourself to considering a closed set of finite integrals. And this is possible and in fact very advantageous. And then finally, another application has to do with single scale integrals. These are integrals, so they just depend on one scale, and therefore the dependence on this scale is just fixed by dimensional analysis. So naively, you cannot find any information about these integrals using differential equations. However, there's some trick how to still find what these integrals are, and you kind of can compute these integrals from nothing. That's why we call it a bootstrap. So I'll tell you how that works, what the idea about that is. Good. So as usual, I encourage you to ask many questions. So just interrupt me whenever something comes up. All right. So yes. So let's start right away with point number 1. In fact, in order to generalize to the multivariable case, let me just take this conjectured formula and rewrite it in a convenient way. So let's take that boxed formula, and I want to write it in differential form. So the differential here just acts on the variable x. And so then we have sum over I d. Actually, let me put the d here, d, and then actually you have to integrate what's written there on the right hand side. But of course, the integral of this factor is just a logarithm, x minus xi. Times f again. Right. So this will be useful to generalize later. But now let's go directly to the multivariable case. Now there's a small issue of notation. I hope you won't get too confused that I would like now to call the variables xi. So please don't confuse these singular points xi we had previously with now the xi are supposed to be a set of kinematic variables. So it could be s, t, and whatever you like. I'm afraid there will be this clash of notation here. So let's not get confused by that. Okay, how do we proceed now? Well, we can repeat what we did earlier for each of those variables. So we can write down partial derivatives d by dxi of our integrals. So they depend on this set of variables. And well, we expect to find this factorized epsilon dependence times some matrix AI, which now only depends on the kinematics. There's a lot of i's around, I'm afraid. F, like so. Moreover, for each of these matrices, we would expect that the singularity structure is as we said before. So only these. Actually, I didn't say before, but the singularities that we had are called regular singularities, which leads to this Fuchsian, in mathematics terms, Fuchsian system of equations. Okay, so now we have these different partial derivatives. There's actually, when you perform the calculation, there's some nice check you can do, which is simply that partial derivatives have to commute. So if you have d, let's actually just abbreviate this by di. So if you have di dj minus dj di acting on f, you have to get 0. As long as you stay away from singular points, of course. And you can use this relation, and it implies some consistency condition for these matrices, which you can check. So again, this is not it's just something which comes out for free if you like, but anyway, it's nice to check. So you get diaj, dj a has to actually in general you get for more complicated epsilon dependence you get one equation, but here thanks to the presence of epsilon we can split it into two independent equations, one of which is this one, and the other one just tells us that the matrices have to commute. So this is a nice check that we can do. Next I would like to, I don't want to work with all these different partial derivatives, that's kind of cumbersome, so I would like to combine them into one equation. Yes?
Why have equivalent equations instead of the sum of this?
Yes, so that's what I said, but let me explain. So in the general case we would have some matrix A prime, and then we'd get this first term of primes minus this term, here equals 0. But now in addition we see that A prime is proportional to epsilon, and you see this first term will be linear in epsilon, second term will be quadratic in epsilon, but we require this to hold for any epsilon.
Does it assume that A is always the same one?
Does it assume that A?
That A is simultaneous A.
Yes, exactly. So here, as I said, in general we get just one equation with basically the sum of these two, but in this case, with this conjecture, it implies that we have two equations.
So the conjecture actually states that the only dependence on dimension isn't the epsilon.
Correct. Yes, and I want to emphasize that here we're still talking about an exact dependence on D, so we haven't expanded.
This looks like a very strong.
Yes, that's right. Yes, it's not completely obvious. let's assume this for now. And as I said, now I'd like to combine all these equations, and the way to do this is to just as here, to write them in differential form, and then the differential of f will contain all these different partial derivatives. Now, in order to do this, we have to perform one integration. So far we've just differentiated, we haven't really had to do a lot of work, but now we need to solve one problem of integration, which is the following. We want to find some matrix A tilde, such that its derivatives give these AI matrices. So d I A tilde is supposed to give AI. Now, here the matrix A tilde would be this one here. And, well, now we'll have a multi-variable generalization of this. So assume we find this space here. Let's say we find such an A tilde. And we can write the differential of f will simply be written as epsilon times d A tilde times f again. So for a given problem, we need to do this one integration. What do we expect to find? Well, we still expect to find that the singularities of this regular time, and which translated itself up there into the fact that A tilde depended on logarithms. So we would expect that A tilde has a following form, that it's some sum over a certain number of terms, that's called J, for again some constant matrices AJ, constant matrices times certain logarithms, and well, the arguments of the logarithms, to be general, I'll call them alpha J, and this will be the analog of the alphabet that we were talking about earlier. So in particular, these alpha J, they can be functions of the kinematic variables. So this is the multivariable analog of the conjecture. So maybe it's easiest to see how this works with some examples. Well, just to give an example different from the one that we had previously, I'll start with a nice case, which is the massless 2-to-2 scattering. So this is something which looks, I think we drew this already, and we'll use it a little later for the purpose of examples. So here we consider some on-shell scattering process, everything massless, at one and at higher loops. And here we just have the Mandelstam variables. And so here, since there are two scale-dependent variables, we have one-dimensionless variable so far. So it's a simple case. I presently moved to multivariable cases, but let's start here. So here one finds so in all of the cases that I'll give, one will find this form of equations. So the non-trivial information, what I have to specify is what is the alphabet in those cases. So that's what's interesting here. So let me do it. Here the alphabet consists actually of only two letters, just as in the example of the previous letter. So here we have of the previous lecture. So here we have an alphabet which consists of x and 1 plus x. And just as we did in earlier lectures, you could analyze and understand the singularities here and identify them with special kinematic limits, s, t, and actually also u going to 0. Okay, but that's a simple example because it depends on one variable. let me just mention that what is remarkable is that, or what's special to this approach is that, I mean, here I drew a one-loop diagram and one finds these equations, but actually, if one goes to higher loops, say you go to 2 loops, or you go to 3 loops, the structure of the equation stays the same. The only thing that changes is the size of the system. So now you have a vector with more components and also larger matrices. So these constant matrices here, they become some bigger n by n matrices. Just to give you a feeling for this, in the one loop case, what would be n? N would be actually 3. If you look at certain 2-loop ladders, then n would be 8. Recall that actually it's still an open problem how to see from the pictures what the number is, but you know, using one of these computer algebra programs, you can just discover it. And then, for example, for this case, I think the number is 26. But in any case, it doesn't really matter. It could just as well have been 100, because then solving these equations is in terms of these iterated integrals is immediate. Okay, so this was one example. So now an example with more variables. Let's look at some 2-variable example. Two-variable example. This also illustrates that actually you can already learn a lot even by looking at one-loop cases where you can identify all the structure. So this is some example for Barber scattering at one loop. So here we have again S and T, but now we also keep the electron mass for these solid lines. And there one can map from those variables to scaleless variables x and y. I'll tell you in a second how we do that. And there one finds the following alphabet. X, 1 plus minus x, y, 1 plus minus y, x plus y, and 1 plus xy. So you see here, this is a truly two-variable case. There's some connection between the variables here. And yeah, so just to complete this, actually x and y are defined exactly in the same way as in our example of the massive triangle. So let's see. So I think we had m squared minus m squared over s was x over 1 minus x squared, and similarly for y, if I recall correctly. So that's a two-variable example, and then perhaps, and you can see that here also with a mass. So in particular, it shows you that this can work also in the massive case. Here actually we went further and looked also at the two-loop case. I won't write the alphabet, but just to tell you what happens is that as opposed to this on-shell 4-point case here, you find more letters. So at two loops, you somehow have access to new singularities in this case. And then some of them are a little bit more complicated than those. So I won't write them now. And then maybe a final example is that I mentioned in the introduction. So if you're interested in vector boson production, again, if you recall, you could have some Feynman diagrams like this, which means that you would have two off-shell variables corresponding to the vector bosons, and you would consider these quarks massless in an approximation, and all internal lines massless. So then, therefore, you would have four variables, ST and the two off-shell vector bosons. That's called P3 squared and P4 squared. So from this, then you can go to three-dimensional variables x, y, and z. And well, here one finds some alphabet which is kind of similar to this one. But of course, as you can imagine, since we now have more variables, it will also contain more letters. And I won't write it here, but they're of the order of 15 letters. It depends a little bit which precise configuration plane or non-planar one looks at. So as if you're interested, it's some paper with Fabrizio Carola, Volodya Smirnov, and Kirill Mernikov. So, but as you can see, so this is just to demonstrate that this actually works, and to give you a few non-trivial examples of how these alphabets look like. Any questions here?
I mean, you could compute this time and
Yes.
Is this procedure simplified, you think?
Yes, absolutely. So,
In what sense?
so here, of course, this is, I mean, of course one can compute this one-loop diagram, and it's known since forever. But what I was saying is that I think in order to understand the method, you can understand it already at this one-loop level, and you will find the structure, and it will help you to find the same structure at higher loops. I think even at the one-loop level, it helps a little bit in the sense that it organizes the answer for this kind of diagram in this nice uniform weight expansion. So this means that it cleans up a little bit the results. You don't have terms with different rational prefactors. So typically the size of the expressions would also, even for known cases, would get smaller. And well, just one place where you can see that it gives you a great convenience is that it's probably easy to compute this integral to finite part and so on. But say you want to know for some reason this integral up to order epsilon to the 17th. Then of course it's possible, but you would have to suffer a little bit in the traditional approach. But here in this approach, the expanding to higher orders in epsilon is very straightforward, and you also guaranteed, since you've identified once and for all what is the class of functions that you need to consider, you guaranteed that within that class of function you can write down the answer. So sometimes this is relevant because, of course, when going to next to leading order, we need to, the way dimensional regularization works, we need to expand up to order epsilon squared, also a one-loop basis. But okay, that one could do in any case, but it's just to illustrate the convenience. But I think in going to higher loops, it's more than a convenience. Especially, well, now of course I haven't written down these alphabets because they're rather cumbersome, but this is precisely the point. In these multivariable cases, if you don't identify the structure, you'd have to deal with partially derivative equations with very cumbersome expressions, and only when you combine them and write them in this form do they become simple. So, well, I mean, maybe just as a rough example. So recently I was considering one case which depended on many variables, and you can just see from the size of the files that you're storing on your computer, you can kind of get an idea for the gaining in understanding. So when you start out just deriving some derivative matrices, this in my case was several hundred megabytes. And then I did this gauge transformation, and it got a little bit better. Maybe it had 1 megabyte, and then I combined further, made sure that I had a minimal alphabet. And then at the end of the day, it's just a few kilobytes. Okay, this is of course not the measure of, not an invariant measure, but it kind of shows you that there's some gaining in understanding here, and that then helps. Yes. So of course, again, this example is trivial, but you can learn a lot from it. And we'll see actually now when we go to the procedure of finding the basis that one can, everything one learns at one loop order can be recited at higher loop orders.
How to compute the initial conditions for the system in multi-dimensional cases?
Yeah, very good question. So I've kind of hinted at this at some point, but let's say it again. So of course you need a boundary condition for integrating. In my experience, usually it's very easy to find some boundary condition because usually there's some singularity where usually you can apply some physical insight to find the boundary condition, and the way it typically goes is that you have some singularities which are unphysical, and you can demand that your functions are well defined at those points. And so that requirement fixes, it depends on the case, either it fixes a certain number of the boundary constants, or in some cases even all of them. So just to make it very concrete, if you're interested in planar 2-to-2 scattering, and this singularity here actually corresponds to a U-channel singularity, which is absent for planar graphs. So you can impose that your solution is regular here, and it fixes all the non-trivial boundary conditions. By that I mean it relates all boundary conditions of such graphs to the ones which are some trivial bubble type graphs, which are just evaluated by gamma functions. So in this project we did not have to compute any boundary condition at all. That's the ideal situation. In some other situations where you do need to compute something, you can still profit from this, and in particular, it's very useful then to have this exact description of the asymptotic limits, because then you can unambiguously compare to some computation in the limits. So what I mean by this is that here's some advantage over fixed order calculations in epsilon, but the fact is that this asymptotic behavior is still exact in the dimension. So in this way you can get around certain order of limits problems. So you see, if you have a term x to the epsilon, there's an order of limit problem whether or not you send x to 0 first or epsilon to 0 first. So if you take this expression and first expand in epsilon, then you lose some information. But here, since our result for the differential equation is exact in epsilon, you still have that information. And that also helps in fixing boundary conditions. Yes, right. So if you, in the multivariable case, in a way it's even simpler, because you have all the partial derivatives. You only need to fix one boundary constant in this multidimensional space. So you can choose whatever limit suits you best. See, you can put all the variables to some constant, the one that you like most. So typically we select some physical limit. Like, remember in the first lecture we said s to 0 for some massive diagram, which was a very simple limit. Here's another example, and so you have a lot of freedom. You just need to know the boundary condition at one point. Along those lines, let me make another comment. To derive these difference equations, we basically just used algebraic properties with integration by parts identities for the graphs. And indeed, only at this level now do we specify the boundary conditions. And you might wonder, so we have some n by n systems, so there are actually n solutions. We're interested here in one solution which corresponds to the Feynman graphs. You could wonder, what are these other solutions? And well, in order to understand this, you could notice that the same derivation that we had also goes through when you place some propagators by delta functions, or in other words, cut propagators. So other solutions of these equations will correspond to certain either directly unitarity cuts or generalized cuts of the Feynman integrals. So if this is another, yes, this might be something which is useful in some contexts. For example, there are people who use the optical theorem in the other way around from the usual one to compute cross sections, and in that case one has to deal with Feynman integrals with cuts. In other words, some propagators replaced by delta functions. And so then this is also possible, and the only thing that would change is the boundary condition. Any more questions? Okay. Oh, we started a little bit later, didn't we? So do you have half an hour? Okay, great. Very good. So now let's see. Now I want to tell you about this point number 2, how to choose a basis. And so really the key property is this uniform weight property, that we want the answer to be expressed in terms of nice functions. And let's just remember what we meant by nice functions. I gave you this example we had some function 1 over x plus y, something along these lines, log x plus some other prefactor, let's say this. It doesn't really matter. Well, the point was that we don't like these rational prefactors or algebraic prefactors because they make this, if they are there, the derivative of this function will be of the same complexity as the function itself. So we like to avoid this, and how to see it in advance. Well, if somebody gave you this function, you might compute some discontinuities which see these logarithms. And you might compute one discontinuity which sees this logarithm and then obtain this rational prefactor here, or compute some other discontinuity which sees this logarithm and find that prefactor. And you would conclude that there are two incompatible prefactors here. So it means that there's no overall prefactor that you can pull out. And this is in distinction to the case of the where we don't have these factors, which is the uniform weight case. So this gives you the idea that applying unitarity cuts can be a tool for seeing in advance whether or not a given Feynman integral can have this property. Now let me show you how this works for some cases with massless diagrams. Let's actually study unitarity cuts for this integral here. 1, 2, 3, P4, and so this depends on S and T as we wrote there. Now I could consider the S channel cut replacing these two propagators by delta functions, but for simplicity, what I would like to do, I'd like to consider both the S and T channel cut, or in other words, I want to compute the maximal cut, where I replace all propagators by delta functions. So this then means that we're integrating close to 4 dimensions. The integration will be saturated by the delta functions, and we can compute the integral just by evaluating the Jacobian on the solutions. I won't do it here, but I just note the result is 1 over S times T. So what this means is that if we want to consider this integral in our basis for the differential equations, we don't like this prefactor, so we should choose as a candidate. We should choose as a candidate S times T times this box here. All right, that's something. Now, of course, this example is very trivial because there's only one way of performing a maximal cut. Because there's only 4 propagators. Where this now becomes more interesting is when we have more propagators. So let's say we have some example of more propagators, say a pentagon integral. If we have a pentagon integral, then, of course, there are 5 different ways of performing maximal cuts. This would be one, and then there are 5 other ones. And you see now what happens is you would, well, let's give these some names. Let's say this is P1, this is K, and this is P2, and so on. Well, now what would this cut give? Well, we'd remove these 4 propagators here because they've become delta functions, but this last one is left. So we would have K plus P1 all squared times the Jacobian, and here we would have to replace K by its value, its special value on the solution. And so this would give some rational prefactor, but it would depend on this cut. So if we take this and rotate it around by 1, we would get actually a different rational prefactor. So this is an indication that this scalar pentagon in 4 dimensions is not a nice function. It's rather a function of this type that we have above. But it's a linear combination of different rational prefactors. So this is something we don't like. Now, what can we do about it? We could make an ansatz. And say, let's take this pentagon. So So it depends on the loop momentum k. And let's insert into the integrand some numerator function which depends on k. And now we make an ansatz for this, so there are many possibilities, but fair enough. And now we consider all these 5 different cuts, and we demand that on each cut we want to find the same prefactor, so that we can pull out an overall factor. And this then, satisfying this requirement would then give a candidate that we can plug into our differential equations. So this one I won't do the computation in detail, but I just want to give a reference, which also contains a lot of nice discussion by Nima and friends. Where they discuss precisely such cuts and some philosophy about these integrals from December some time ago already. So especially the first few chapters of this paper are very readable and give a nice introduction to this. And particularly you'll find then the solution to what I just told you, for what is a nice pentagon, a nice numerator for such a pentagon integral. And well, just to reiterate, then the idea is to here, following this approach, we very easily find some set of candidate integrals which we can then use as the master integrals in our basis. So we then change basis from whatever basis we had before to this one. And you see, the good news is that we might let's assume we made a mistake here, or something didn't quite work out as we wanted to. We can then just plugging this into the differential equation, we can check whether or not we have a good basis. Because once we find this form, then we're done. Then we've proven that we will have this uniform weight integrals. So this is a very useful tool. It's actually not important whether or not whether or not you can prove at this point that you have a uniform weight integral, because you have a very strong test. At this level, you either get the right answer or not. Sometimes you almost get the right answer, just as in this example here, that there are some extra terms that you still need to integrate out, but typically it will almost give you the right form. So this is what makes it very useful. So now these were some one-loop examples, but I wanted to show you how just understanding the simple one-loop cases actually helps you a lot. You can recycle everything that you learned at the one-loop order and immediately go to the next loop. And likewise if you want to go to higher loops. So let me show this for this two-loop masters case, where you consider this family of ladder integrals. So there, as I said, there are 8 integrals in total. Now there's one new aspect in this sector of 7 propagator integrals. It turns out that one needs 2 master integrals in this for the 7 propagator segment. So, alright, let's see if we can find 2 of them. So, an easy thing to do is to take this double box, and we know what happens if we cut a 4-point subintegral. We can replace it by this Jacobian factor as 1 over S and T. We just have to be a little bit careful because this momentum is P4. Let's say this is K1. So if we localize the K2 integration, then what changes is that now, well, S will still be the same. So the Jacobian here that we get is 1 over S, but T is now something different. T is is actually K1 minus P4 squared. Right? So we're just taking the relevant kinematics for this subintegral. And so therefore then the result of the cut will be, I just copy the uncut propagators here. And then we need to, well, we have this 1 over S over all, but we need to insert this into the integrand for the next loop. And, well, this happens to be just this propagator here. Right, so then we have K1 So we see that this cut just gives us back the one loop box. We know the one loop box already, so we could continue cutting now. So the result of the cutting one more time would give us another s times t, so we get s squared over t. So which would suggest that we can make a little note here on the side that this double box times s squared times t, that's a candidate that we should use. So it's one of the two candidates that we will choose. But we need another one. What to do to find the next one? Well, to find the next one, we have to go back to one loop actually, and we went through it a little bit quickly, but you can realize that actually the triangle integral is also a good, the triangle integral times s actually is also a good basis element at one loop. So let's assume we know that already, and let's try to use it at the two loop level. Now let's look again at this cut. Actually, when we cut these four propagators, the three propagators that are left, they actually form a triangle, and the only reason we get a box is that there's this factor coming from the Jacobian. So, is there a way of deleting this factor? Well, we could get rid of it if we, in the original integral, if we insert a numerator, which is designed to cancel it. So let's consider this original integral, k1 and p4 like so, and just insert k1 minus p4 squared in the numerator. Well then, performing the same cut, we get 1 over s times the triangle, and we know from cutting the triangle this will give another 1 over s. So we see that we just have to normalize this by another factor of s squared, and then we get a unit value for this leading singularity, for this maximal cut. So this would then be our candidate for the second integral that we need. And again, so here you know, just from this simple analysis, you would end up with these two integrals, but you can then immediately prove that you made the right choice by plugging them into the differential equation. And as I explained, this is all completely automatic. Maybe let me just make one. Shall I do a further example?
Is there a quick way to see that we need two most integrals for this topology?
Yeah, good question. Well, I've been thinking already for half a minute, so actually I don't think at least I don't see an easy way. And in fact, if we generalize to, so this is the case where we have all on-shell external legs. You could actually generalize to some legs being off-shell, like we need for this vector boson production. And then it happens that the number of master integrals you need can sometimes be higher. Because, well, this is basically because this configuration is very symmetric. So if you break the symmetry, then actually, so this has some symmetry under flips, and then you need a third one. Maybe that's obvious, okay. But yeah, I don't have it's not obvious a priori. And more generally, at higher loops, you can have even more than two. I know some cases, for example, at some moment, we looked at some free loop non-planar integrals like this, and there it turns out that you need 7 integrals at once. But yeah, so just when I said there's no good, I don't know a priori way of finding this. I don't think it's settled. If you want to read up a little bit more about it, there's a nice paper by Roman Lee and probably a co-author. So there's one paper where they prove that the number of master integrals is finite. So either in this paper or in a later paper, they comment more on these numbers. Okay. Well, maybe this example is actually a little bit simple. Let me go and do one more example, which is a little bit less trivial. I don't want to erase that. Erase this.
How does the counting depend if you have a scalar theory of U or the gravity?
No, it does not. So here actually none of what we're doing depends on the specific theory, in the sense that for one particular topology of Feynman integrals, we compute all of them, and then you could use them to express results in any theory that you would like. It's true, however, that if one considers special theories, such as supersymmetric ones, one may not need certain of the integrals, so then one needs only a subset of them. This becomes relevant, for example, in the case where one only needs finite integrals. But it doesn't. This approach doesn't depend on the theory in the sense that we just compute the complete basis. So then, if you have some scattering process which has the same topology, you can use the result. So I just want to give one further example of this, where it's actually slightly more interesting. So this is the case of the non-planar double box, which seems more complicated, but as you will see, you can use exactly the same idea. Now, let me give some names again to the external momenta, P1, P2, P3, P4, for ingoing, and that's again called, let's call this K1, or let's put it like this. Now, I don't know how familiar you are with non-planar integrals. It's actually, sometimes it's fun, sometimes it's mind-boggling, but so we can redraw this a little bit. And I want to move this vertex on the inside here. Let's see if I manage. So I want to draw this. Let's see. So I've copied the part on the left, and I've basically this vertex here used to be over there, and I've pulled this inside, and this one is there. Okay, so it's just a different way of drawing this. And what it makes obvious is that here we have one subloop which has 5 propagators and another one which has 4. So, of course, now there are various ways of analyzing this, but just to keep things simple, we'll cut the box subintegral. Right? That's the easiest thing that we can do. So let's cut the box subintegral. We already know that Jacobian is this, from the Jacobian we get this 1 over st factor, but of course we have to replace the momenta by the momenta that flow into this box. So here one of them is P4 minus K1, just as previously, K1 minus P4 squared, and the other one is K1 minus P3 squared. So you see what changes is that now both of these factors depend on the remaining loop momentum. So what this means is what we'll obtain is some object, well, which has these original 3 propagators times these two extra factors. There's a reason I'm not drawing it. Well, you could draw some pentagon integral, but it would be some funny pentagon integral with some funny momenta flowing in and out. This is like this because it came from a non-planar diagram. But however you draw it, it's something which has 5 propagators. Now we can remember the analysis we did. I think here it was that we did for one loop pentagon. We saw that the scalar one loop pentagon is not a nice object. So we could now continue to cut, but we already know what the conclusion is, that this is not a good basis element. So what to do? Well, we want fewer propagators. So the idea is to simply remove some of those by putting in appropriate numerator factors. And from what we did earlier in the planar case, you can now immediately write down 3 possible numerator factors. Well, one possibility would be just to delete one of these factors, and then we would get a box here. Or we could delete the other one. Or actually, we can also put a numerator which deletes both of them, and then we end up with a triangle. So this immediately gives us 3 candidates that we can use for our differential equations. And so it turned out in this project with the vector boson production of these 2 off-shell legs, we actually needed to use exactly these 3 numerators. But as you can see, it's very easy to find them. But then using them in the differential equation makes a big difference, because it takes you from some complicated form of equations to this very simple one that I had here in the conjecture. Okay, so I think that this should suffice for the examples, and so in the 10 minutes that remain, I'd like to just give you an idea for what these 2 points are. So let's see. So I'll just explain the idea. Hopefully, we'll not need technical details. So what about the case when we have finite integrals? So we said already earlier that one of the strong points of this method is that it gives you a lot of information. It gives you the whole epsilon dependence. If you wanted to, you could perform to whatever order you like the epsilon expansion. But in some cases we don't want this, and it's actually unnecessary information. It makes life more complicated. So this could be in n equals 4 supermills if we have some setup which is manifestly finite, or it could actually be also in some more applied cases. Maybe you have some infrared safe quantities in some physical application, and you already know that you have a manifestly finite result. So in that case, the question is, can we use the same method but without dragging along epsilon? And so one example would be, and so this is something we considered with Simon Caron-Giraud in a paper from earlier this year. So there we considered some light by light scattering in our favorite toy model, n equals 4 supermills. And basically what you get looks like this. So you have some 4-point amplitudes, planar, with some mass running in the loop. So the mass, we keep the exact mass dependence, and thanks to the mass, this is just infrared finite. And well, because it's in n equals 4 supermills, it's also UV finite. So this is a nice setup where you might want to consider such a method. And well, it turns out actually at the one loop order, we needed to find exactly this one loop box integral here. So this is finite in 4 dimensions. You can of course compute it using that method, but let's see what happens if you compute it directly in 4 dimensions. And so the idea is, if you start with some finite integral such as this one, all we want to do is take derivatives. So in principle, taking derivatives does not introduce divergences. However, we have to be very careful in our manipulations, because usually when using integration by parts, we split up what we get. How to put it? It often happens that we split up a finite term in terms of a number of them which are individually divergent. And so now we have to be careful. If we want a setup which operates in 4 dimensions, we have to make sure that each of the terms is individually finite. But anyway, it's possible. And if one follows this through, one can actually obtain the same type of differential equations with, again, a minor difference. And let me write the result. So you find that you can set this up just in 4 dimensions. And you find the following. You find that the differential now is again the differential of some matrix A tilde times F. And, well, it's actually the same equation we wrote earlier, but now I've removed epsilon. All right. If I just tell you this makes it sound very complicated. But now, actually, thanks to living in 4 dimensions, this matrix A tilde now is simpler as before. It's probably easiest to show you what this matrix A tilde is by drawing some diagram. Let's say we start with this massive box integral. Well, so this depends on s over m squared and t over m squared. So we can take 2 independent derivatives. Let's say we take 1 derivative. Then actually we get some finite bubble integrals, which look like this. They have some power 2 to make them UV finite. It comes from the differentiation, so that they can live in the S over T channel. So importantly, the arrow goes down. We don't get the same integral again. I'll explain in a minute what these different levels mean. But anyway, then starting from the bubble integral, we can take another derivative. And here we find actually this tadpole integral, which we already encountered in previous lectures. And if you remember this tadpole integral, the way we normalize it, it's actually equal to 1, the function 1. So, so now we see what happens in terms of weight. If we look at, and this is all we need. So this is the full differential system. So you see we start with the simplest function you could imagine, 1. Well, this has weight 0. And then, in order to get from here to the next level, we have to integrate, we have to go back up one of these arrows, which corresponds to integrating this against this kernel here, which increases the weight by 1. So these bubbles, there's certain logarithms, they have weight 1. And then finally, going up to the box, we just have to follow back up the arrows. There are two possible paths, and we get the weight 2 function, so that the box in fact is some combination of dilogarithms. And well, think about this more carefully. The box in fact is given by 2 terms which correspond to the 2 ways of integrating back up here. Now, just as before, this is a simple one-loop example, but this is actually what allowed us to go a lot higher, and we actually applied this all the way to 3 loops. And this is certainly something which would not have been possible in the full D-dimensional approach. So here one gains really a lot from the fact that one doesn't have to keep higher order terms in epsilon. So now my time is running out, so maybe in the 1 minute that remains, I'll just briefly explain the idea of the bootstrap, and then I'll finish. Well, the idea is actually very simple. Say you have some single scale integral like this, some form factor integral. Depends on momentum P1, P2, so you just have some variable S like this. And well, the integral by dimensional analysis, it will just be some number, f of epsilon times s to some power. So differentiating in s doesn't gain you anything. You just can check this power here. So the idea is, what if you make the problem a little bit more complicated so that we can apply our technique? Let's just say we define the same problem now for P1 squared different from 0. So then we have access to this whole machinery, and well, you can define everything in terms of P1 squared over S. Let me tell you what you find. You find that you can for this new function of x, then you can find this canonical form of the differential equations, like so. A preferred simplest case, in fact. So we have this equation. Now, the case we're actually interested in, we're interested in the x to 0 limit. So if we take that limit, we go back to the original problem. So the information we want is contained in there. However, now you see we have this extra singular point at x equals -1. And it turns out that this extra singular point is a very simple one. X equals -1 is a simple limit. In fact, this is what I was telling about earlier. It's not so easy to explain now, but it turns out that in this limit you can get the boundary conditions for free. So it's one of, remember I explained it here for the case of this U-channel singularity, that this was a singular point where we could just get the boundary condition without working. Now, without explaining it here, it happens that this is also the case in this problem. So we can just fix the boundary condition from this point without doing calculations. And then what we have to do is we have to transport back that boundary information from this point to the original point over here. But this is just some simple integral in this alphabet. These are just these harmonic polylogarithms which we had evaluated at unit arguments. So this is something completely known. It's evaluated in terms of zeta values. So in this way you can get the result for the original integral without having to do any calculation really. I mean, just from knowing these matrices A and B. And so we have this situation, we're interested in point 0, and we have a solution at -1, and we just integrate back using the differential equation. I'd like to mention that this is actually something very common in mathematics. Well, this question is called a Knischnik-Samologikov equation, and what one is computing here is transporting the boundary value from one point to the other is known under the name of Drinfeld associated. So it's some object which just depends on the matrices A and B. In terms of those matrices, it can be expanded in terms of those matrices and zeta values. And so it's precisely this associator which then gives the value for the original integrals here. So it's just as an idea, and why it works really is what I said earlier, that the differential equations somehow they like to give you the boundary conditions for free. You can kind of you can get them often without doing any calculations. So around a few minutes over time, I think I'll stop here. Thank you very much.